Hello everyone, my name is Siwen. I would like to present my work, Effects of Water Absorption on Mercury Contamination in Fiberbank Sediments using X-ray fluorescence spectrometer. This is our research group, Radiation Sensor Systems at Sweden University. In the manufacture of paper and pulp industry, large amount of contaminated cellulose and wood fiber materials were released directly into the sea and lakes. Discharge of untreated paper and pulp industry wastewater have caused large environmental impact on the sediments along the coast. Fiber-rich sediments are found close to the industrial factories, which are highly affected by the persistent organic pollutant contamination. Over time, it gradually built up and created fiberbank deposits. The contaminated fiber material eventually accumulated on the seabed, as shown in the left figure. Since 2010, the county administrative roads in Norrland and the Swedish Geological Survey has made an inventory of 39 areas in connection with activities that may have caused the fiber emissions. In 28 of these, fiber sediments were found near the factory or at the mouth of the discharge pipes. However, all the black points on the map remains to be further investigated. Since many chemicals were used or could be formed in the process, the pollution level in fiber sediments are often elevated and exceed the guideline values. The level of different pollutants varies between the areas, depending on which chemical and which process has been used. For example, the highest level of dioxins and mercury occurs along the coast of Bosnia Sea. Elemental mercury was historically used in the paper and pulp manufacturing process, but the use of mercury in industry process is now banned in the EU countries. Bacteria that thrive in white and low oxygen environment, such as lake bottom, could transfer elemental mercury into its most toxic form, mercury. Mass mercury in water can be easily bioaccumulated in aquatic food chains and eventually consumed by human beings. Exposure to high concentration of mass mercury damages the immune system and the nervous system. Thus, understanding the total concentration of mercury in fiberbank sediments is essential for environmental assessment and monitoring. Analysis of mercury in environmental samples is a sequential process involving extraction or pre-concentration, separation, and detection steps. There are different methods of separating mercury from the sample and for measuring the level of mercury. All methods rely on extracting elemental mercury into a vapor, such as cold vapor, where free mercury atoms in a carrier gas are excited by an ultraviolet light source, or using the thermal decomposition and inductively coupled plasma. The analysis techniques are various. However, all these laboratory analytical methods require pre-treatment process of the soil and sediment samples with acid digestion. This step is time-consuming and easily causes the inputs of cross-contamination among samples. Rapid screening technique for detection of mercury in a variety of environmental samples is desired. In addition to these techniques, X-ray fluorescence is a widely used in field application when screening for high concentration of metal in the entity in different areas. Handheld XF technique is already a proven method to detect mercury from electric or electronic products for compliance with the EU restriction for hazard substance directive. This is also widely used as a first screening step for mercury contamination in soil and sediment samples, and in some cases of confirmatory testing. Overall, the XF field technique provides a significant improvement over current practices to detect mercury contamination. When a material is irradiated by X-rays, the incident X-ray photon with high energy can inject the electron from its atomic orbit, leaving the atom in an unstable status. To fill this space, an outer shell electron can fall into an empty position of the injected electron. The falling electron emits a characteristic fluorescent X-ray photon. The energy difference of the two involving shells are unique and can be used to identify that material. This phenomenon is widely used for elemental analysis and chemical analysis. In general, the XF analysis technique offers a quick, real-time, and cost-effective way of screening surface contamination. A typical XF setup includes an X-ray tube to generate primary X-ray beam to the sample surface, and a detector is used to record the fluorescence radiation coming from the sample. This figure shows the XF spectrum of pure mercury, which is obtained by handheld XF device Bruker Tracer 5i. In this spectrum, each peak corresponding to a characteristic emission line from mercury, and the table below lists all the possible X-ray transition lines of mercury. The strongest line in each shell is assigned to the relative intensity of 100. For underwater measurements, the water absorption will strongly affect the photon intensity. So for the low energy, such as the ion of mercury around 10 kiloelectronvolts, they are easily absorbed by the water. In this work, the K-alpha 1 line was chosen to determine mercury due to both the high energy and the high relative intensity. To excite the K-alpha line of mercury, a higher X-ray source is needed. We investigate a radioactive cobalt-57 source, providing 122 kiloelectronvolts photons as its main energy line. However, for high-energy photons, the generated background signal is stronger than for low energies. The background signal in an XF spectrum originates from the scattering of primary photon by the sample surface. For in situ XF analysis, the water surrounding the sediments introduce the scattered background noise, which gives a rise to a poor limit of detection in the XF measurements. As shown in the blue line without filter, the full spectrum from low energy to high energies overlaps with the peak from Mercury, and then the intensity of the Mercury will be underestimated since these peaks might be hidden in the spectrum. A suitable filter foil placed in front of the primary X-ray source can significantly improve the sensitivity in an XF analysis. The most important consideration in selecting the optimal filter material is that the filter absorbs the continuous background radiation by using the absorption age of that material. The performance of 6 filter foils were compared in the MCMP simulation. The inset shows the absorption age of these materials. And as we could see, the absorption age of tungsten, shown as a purple color, is at 69.5 kilo-electron-volts, which overlaps with the Mercury K-alpha line peak, and also is very close to the K-alpha 1 peak. So tungsten filter is not the optimal filter for mercury detection in an XF measurement. The materials such as gas, wood, and rubber absorbs relatively less X-rays. Conversely, even very thin sheets of heavy metals absorb nearly all X-ray incidents upon them. Thus, by applying an X-ray filter, the intensity of the X-ray signal is decreased with the thickness of the filter increasing. Thus, the measuring time is increased. So there is a trade-off between the high sensitivity and short measurement time for a practical XF setup. The filter's transmission values for the 6 filter at 122 kilo-electron-volts are listed. As expected, the filter strongly reduced the intensity of the primary beam. A 3.5 millimeters silver filter reserves a relatively good photon flag transmission, which was chosen for further test in the water influence measurement. In order to study the water influence in the XF measurement, 14 thicknesses of water layer are compared in the range from 0 centimeter to 2.25 centimeter. Geometry models of the XF setup used for MCMP simulation is shown in these figures. The procedure starts with the definition of a filtered X-ray source emitting X-rays towards the center of the top surface of the sample. The sample is a solution with the mercury concentration at 1000 ppm, which is covered by an additional water layer. The XF spectrum from varying water layer thickness were obtained. The inset shows that the mercury K-alpha 1 peak is decreased by increasing the thickness of the water, while the background scattering noise is increasing. The highest scattered background was achieved when the water thickness is 3.25 centimeters. As a result, the water content surrounding the sample caused a reduction in precision and a lower accuracy for detecting mercury in an XF system. It should be noted that the source peak at 122 kilo-electron-volts results in a Compton scattering peak at 82.5 kilo-electron-volts when the scattering angle is 180 degrees. Instead of mercury peak intensity, the peak to background ratio were calculated, where the background counts were computed by the average of the pre-peak and the post-peak background. With the water absorber thickness increasing, the peak to background of the Mercury peak is decreasing exponentially, as shown in the right figure. We identify that the limit of detection for this system is when the peak to background ratio is larger than 3, which means that the characteristic peak of Mercury at a concentration is greater than above the random variation in the background. Thus, the detection range is the water thickness below 1.5 centimeters for detecting a 1000 ppm mercury sample. The scattered radiation and the variation of water content in Fiberbank sediments are crucial factors for in situ XF analysis. Tests on future materials showed that an optimal primary X-ray filter can reduce the scattered background noise for a specific energy range, and thus improving the sensitivity of the XF system. The degree improvement is determined by the X-ray absorption age, which is controlled by the filter, by the filter's material and the filter thickness. Simulation on a series of water thickness demonstrated that an increase in water content caused a significant decrease in the XF sensitivity due to the absorption of the characteristic X-ray line from the sample, and the water also produced a stronger scattered background noise of the primary radiation. The detection range in water is 1.5 centimeters for detecting a 1000 ppm mercury sample. In a practical setup mounting, a shorter distance between the primary X-ray beam to the sample and the sample to the spectrometer is desired. Thank you for listening.